As data generation accelerates, traditional single-server architectures hit a hard physical limit. There is only so much storage and processing power one machine can hold before the volume of incoming data begins to overwhelm the hardware. A distributed computing cluster bypasses this bottleneck by spreading the storage and processing load across dozens or even thousands of interconnected standard machines. This distribution relies on the Hadoop Distributed File System, or HDFS. HDFS breaks large datasets into smaller blocks and replicates them across multiple machines, creating a storage layer with built-in redundancy. MapReduce and YARN sit on top of that storage layer. MapReduce breaks processing tasks into smaller subtasks that run in parallel, while YARN manages the system resources, deciding which machine gets the CPU and memory needed for each job. HDFS and YARN provide the core power of the cluster, but specialized enterprise tasks like real-time ingestion or complex data transformations require a suite of integrated tools to handle the specific needs of the data. Building a complete big data solution involves deploying specialized components like Hive, Pig, HBase, Sqoop, Flume, and Oozie. To understand these components, we will follow the life cycle of data as it travels left to right, from its raw state outside the cluster to its final analytical query. We will trace this flow using the architectural model developed by the data engineering team at Royal Research. Mastering the Hadoop ecosystem is a matter of seeing how these tools snap together to move and mutate data as it passes through the pipeline. The process begins at the leftmost edge of our pipeline, where data must be imported from external sources into HDFS. The first challenge involves migrating structured data from traditional relational databases, such as MySQL or Oracle. Apache Sqoop handles this by acting as a bridge for bulk transfers. It automates the import process and supports incremental loads, pulling only the records that have changed since the last transfer. Conversely, web servers generate a continuous stream of unstructured log data that requires a different method of ingestion. Apache Flume captures this streaming data. It is a distributed system designed to collect and aggregate high-volume logs, moving them into the cluster in a steady flow. Flume focuses on reliability and recoverability, ensuring that even if an individual node fails, the data stream is preserved and eventually delivered to its destination. Together, Sqoop and Flume normalize vastly different data velocities and structures, allowing them to coexist within the same Hadoop environment. From the ingestion zone, data lands in HDFS for bulk storage. While HDFS excels at holding massive datasets for batch processing, it cannot provide real-time, random read or write access to individual records. Apache HBase solves this limitation. It is a NoSQL database sitting directly on top of HDFS to provide immediate access to specific data points. HBase uses column-oriented storage rather than row-oriented storage found in traditional databases. This reorientation optimizes random access performance. When a query targets a specific attribute, the system only reads the relevant columns, bypassing scanning entire rows. This structure provides strong consistency for read and write operations, and the system scales horizontally as you add more nodes to the cluster. HDFS provides massive scale to hold the data, while HBase provides the surgical access required for online analytics and transaction processing. As data moves into the processing phase, much of it remains in a raw, mismatched state. It requires a transformation layer before it can be used for business analysis. Apache Pig handles this extract, transform, and load, or ETL, labor. Developers use a high-level scripting language called Pig Latin to express complex data flows, abstracting the complexity of underlying MapReduce jobs into a readable script. For highly specialized processing, developers can extend Pig's capabilities with user-defined functions. The raw data passes through the script and emerges as a clean, structured dataset. Pig acts as the industrial refinery of the ecosystem, performing the programmatic work of converting messy, raw inputs into structured formats. Once the data is structured, it moves into the final stage of processing for interactive reporting. Apache Hive provides the data warehouse infrastructure for this stage, sitting atop the Hadoop cluster. Analysts use a SQL-like language called HiveQL to query data. Hive translates these queries into MapReduce jobs, removing the need to write low-level code. This system relies on schema on read. As shown here, Hive does not check the data structure when stored. It applies a schema only at the moment the query is executed. This contrasts with traditional relational databases, which require a rigid schema to be defined and enforced at the time the data is written. Hive integrates directly with HDFS, allowing it to pull only the specific blocks of data needed to satisfy a query. This enables analysts with standard SQL knowledge to query petabytes of data directly, without writing any underlying Java code. Pulling back to see the entire pipeline reveals a logistical challenge: the timing of these individual tasks. Architects must ensure that Flume finishes ingestion before Pig starts transforming, and that Pig completes its work before Hive generates a report. Apache Oozie manages dependencies. It's a workflow scheduler organizing Hadoop jobs into a logical sequence, ensuring each task waits for its predecessor to complete. Oozie uses time and data triggers to orchestrate this order, optimizing resource utilization across the cluster. Oozie serves as the operational glue, converting isolated tools into an automated, hands-free enterprise workflow. A robust big data solution functions through a coordinated sequence of specialized tools. It starts with structured and unstructured ingestion through Sqoop and Flume. Data then moves into tiered storage, using HDFS for scale and HBase for real-time access. Transformation and analysis follow, with Pig refining the raw data and Hive providing an interface for querying. Oozie maintains the master orchestration, ensuring every job runs in the correct sequence. By arranging these modular components into a contiguous pipeline, engineers can build fault-tolerant systems capable of driving innovation at any scale.